Welcome to a new video about circuit design. This is our example number 4 in this design series. We will discuss in this case a typical example where we need a specific current in a branch, and this will be our situation for this case. Of course, we will look at the calculation, also the simulations in SPICE to verify our calculations. So this is the circuit we have given. There's an electric circuit given here with R1 of 20 ohms here, and R2 of 50 ohms, that's here, and also R3 of 100 ohms. There's also a current source given of 80 milliamps. In this case, we want to determine the values of Vs and the R4 such that the Ix that's shown here, going from left to right in this branch, is 20 milliamps. So we have two unknowns and we have a couple of given here. So how can we work this out? Let's look at the solutions. Now, before we move on, let's also define for ourselves which method we will use. I prefer to use, personally, the node voltage analysis, but you can also do that here using superposition principle or the mesh current method. So that's also fine. But I think this one is much faster. So I first determine the nodes. In the case I don't know the voltage. At this node I don't know the voltage, so I call it A. And also this node I don't know the voltage, so I call this B. Okay, now I also designate a plus and a minus sign. This is what I have chosen, so plus and minus sign for this. I1, I2 goes in that direction, which is actually the same as Ix, because this is series, same branch. This is I3, so in this form, and this is I4. So I have now given the also directions for the currents. Okay. The next step is step 2, write down the Kirchhoff's current law for each node. We have two nodes, so we will develop two equations from this Kirchhoff current law. Now, Kirchhoff current law at A is given by I3 will be generated or created by I1 plus IP. So I can say I3 is I1 plus IP. We know IP, so we need to then rewrite this in terms of voltages and resistors. So that's V3 over R3 is equal to V1 over R1 plus IP. Now V3 we also need to write it down in terms of Vs, Va and or Vb. Now we can say this voltage V3 here is actually between the node A and B. So we can also say Va minus Vb over the resistor R3, that is I3. I1, that's this current, is this voltage, which is the same as Vs, minus Va, and that will be then divided by R1, will give you I1. Now IP is already given, so we don't have to write it down in voltages and resistors. Now let's then substitute the values. We have here 100 for R3, 20 for R1, and then 0.08, so 8 milliamps given in amps for IP. And we have still three unknowns here, so VA, VB, and Vs we don't know. And Vs is of course what we really want to know for this example. Okay, if I now multiply the left and the right hand side of this equation by 100, I can get rid of these fractions. I get Va minus Vb, and also this will be then 100 over 20 will be 5. This will be times 100, will get 8. If I now work out these parentheses and also move everything to the, let's say, to the left hand side, I will get this equation. So I will get 5 times Vs, will be moving to the left side, will be then minus 5 times Vs. I get minus 5 times Va, there will be then plus 5 times Va. On the left side, it will be then 6 times, including that one, you'll get this equation. Now let's call this equation number 1, and then we will use it later. Now, we develop now the Kirchhoff current law equation at node B, and I can see I3 and I2 come at this node and will produce I4. So we can say I4 is equal to I3 plus I2 or Ix. I prefer to use Ix because we want that, and that is something already given for Ix. Now we can again write these equations using volts, the voltages and the resistors. So V4 over R4 is equal to V3 over R3 plus Ix. Now V4 is Vb. That's already given from this node to the ground, so which is Vb. So Vb minus 0, Vb. And this is then V3, which is exact same as before, so which is actually Va minus Vb. Now, and Ix of course given. We can of course given a relationship here also using Ohm's law, but let's keep it in this form because we know the voltage, the current value. So we have now VB over this. R4 is not known, that's still of course an unknown, but we know R3, which is 100. And we also know the 0.02 for RIX, the current. That's 20 milliamps. Okay, if I now multiply again the left and right hand side by 100, I get this expression. And you see now also two unknowns, VA and VB, but also the third unknown, the R4. So in total, it looks like we have two equations. Let's call this equation number 2. So we have here 3 unknowns and another one is R4. So it looks like we have 4 unknowns using 2 equations. Can we develop another equation? We can. We can develop another equation using Ohm's law here for I2, which is also same as IX. So we can say IX is equal to V2 over R2, because that's this voltage. And that is then Vs minus Vb over R2. Because this voltage node is exact same as the voltage node, so this is then Vs. And this will help us because we know R2 and we also know Ix. So if I go to 0.02, it's equal to Vs minus Vb over 50, I must say. And if I now do 50 times left and the right hand side, I will get rid of this fraction. It will be 1 exactly equal to Vs minus Vb. And that will give me Vs is equal to 1 plus Vb. So we have another equation, another form where the unknowns are also given. And that is then the third equation actually. So we have now 3 equations, but still 4 unknowns. So Vs we don't know, Va, Vb and also the R4. So we can solve this, but we will need to select one of the unknowns because we don't have a unique solution. In order to have a unique solution, you need a fourth equation. So we need the 4 equations if you have 4 unknowns. If you have 20 unknowns, you need 20 equations to get a unique solution. So we can say the following then. Substitute this 3 in this equation number 1. So in here, so what you get is the following. 6 times Va minus Vb minus 5 times this. That's shown here. So if I now work out the parentheses, you will get minus 5 and then minus 5 times the Vb. So it's still equal to 8. Now you can now collect the terms, and also this minus 5 can be replaced to right hand side will be plus 5, so it will be 13. And this is then minus Vb, and minus 5 will be minus 6 Vb. So you'll get 6 times Va minus 6 times Vb is equal to 13. Okay, this is now another equation, and we can call this equation number 4. And this equation has only 2 unknowns, Va and Vb. And this equation has 3 unknowns, but still we can say there are still 3 unknowns. So we have 2 equations and 3 unknowns. So we need to still select a component value or one of the voltages. So let's bring these 2 equations together, and this is what we have mathematically given. And you see again 2 equations, equation number 2 and 4, but 3 unknowns. So we can say this condition: 3 unknowns, Va, Vb and R4 are not known, but we have only 2 equations. So we need to select the proper value for one of the 3 unknowns. So you can of course not take a negative value, for example, for R4, or if you take a, let's say 0, that will also make this not defined. So it must be a proper value. So let's select a value, and I have chosen actually for R4 to select 100, just easy, so I will get rid of this 100. So 100 over 100 will be just Vb, and I will actually make then this equation number 2, Vb is equal to Va minus Vb plus 2. Now I can now rewrite this, replace this Va to the left side and also the minus Vb to the left side. I will get this. Now this 2 is still there on right side as a constant, so this will be in our equation number 5. Now this is fine. I have an equation now, 5th equation, where you see the Va and Vb as 2 unknowns, but I have also an equation there, equation number 4, which has also 2 unknowns, the same unknown. So I can then make a set of equations using equation number 4 and 5 and bring this together on top of each other, and then we can solve this. Now, I want, of course, solve the situation such that I have the Vs, and Vs was given in terms of Vb. So it is better to keep the Vb here and then actually eliminate Va. So I will multiply this by 1, just keep this, and the second one by 6. So I will keep it, the first one, I will multiply this by 6, so the minus 6 VA plus 12 VB is equal to 12. So if I now add them up, because I want to get rid of this, add them up, there will be 25, that will be plus 6 VB, and that will give me 0 VA. Now, in order to calculate VB, I will need to 25 over 6. That will give me 25 over 6 volts, or approximately 4.167 volts. That is what we have. Now, then we get from equation number 3, which is not shown here, but it was in the previous slide, that was Vs is equal to 1 plus Vb. So we need to add just 1 to this answer for Vb. So if I do it exactly, it will be this one, and it will be then 31 over 6, that's the exact value, approximately 5.167 volts. So, and we will use this value to verify this shortly in the simulations. So in summary, we have now chosen R4, and from there the consequence was Vs is 5.167. If you take another value, you will get, of course, another value also for Vs. So you can also say, I would like to select VA, and then you need to calculate the rest of the parameters. That is also perfectly fine. This is just what I have chosen for this case. Okay, now let's now go to the simulation result. These are now the simulation result. You can see here the circuit and also the summary of our results. This is of course what we wanted, Vs and R4, that's all shown here. Now you can see the simulation. This is the diagram I have prepared in the simulator. This is where I measure the current, Ix. This is the current arrow to measure the current in this branch. You can see it's 20 milliamps for this value. So we have now proven that this is indeed correct. And you can also click on that component. I will show you that shortly also in SPICE. You can see it's also 20 milliamps and the corresponding voltage is 1 volt. Let's also do that in the SPICE simulator and also see how we can generate these values there also. But we can already say it is proven or verified that our calculations are correct. But let's now go to the SPICE simulator and also there briefly discuss this. So let's jump to SPICE simulator. All right, we are now in the SPICE simulator. You can see here the voltage, which was approximately 5.167 volts. We have here the R1, which is 20, R2 was 50, R3 was 100, and this is what we have selected as 100. This is the current arrow, so you can take an arrow from the meter, that's actually shown here. This is a current arrow, and you can change the name, etc., and then measure the specific current here. The current flows from left to right, so it's also the arrow shown here. This is the current source IP, 80 milliamps. Okay, what I want to do is I want to really verify this. Now let's go to analysis, DC analysis, and then do the calculate node voltages. That's what you do, and you get the results directly, which you actually find in the measurements here, and that is 20 milliamps. You can also click on this. That's actually what I have shown in the slide presentation. That was actually 20 milliamps also here, exactly as shown here. What you also can do, you can also do a table of results. So that's exactly same. You make a table of results, and you can click on this one. You also see 20 milliamps, you highlight it in red. But let me also discuss the following. If I, for example, take a less accurate value for this, this was not exact value. This is of course 31 over 6, and this was, let's say, what I have just typed in here, 5.1666, a lot of 6. But if I now do, for example, 5.17, less accurate than in this case. What is the current here? Let's see if it is 20 milliamps or different. Now you get now 20 milliamps, a little bit more than 20 milliamps, 20.017 milliamps. It's also shown here. So that is really the consequence if you don't take accurate results in your simulations. Of course, you can say this is perfectly fine for my analysis, and then you can take 5.17. But if of course take it even less accurate, make it larger, 5.2 for example, and again measure it, you can see it goes up. So you can also see, will it go up if I increase this voltage? Sure, because you're now creating actually more voltage across these two nodes, and that will also create more current through the resistor. So you can of course go to, for example, to 10, maybe more, larger, and see what's happening, and you go up by your current. That's just to show you that it is indeed happening. So we will take this. This is the more accurate value. What you can do is just type in 5.166, a lot of 6 here. And if I now do this, it will of course round it up by itself, so it is already doing the simulator by itself. And you will now get that 20 milliamps. Alright guys, this is for this example, verified also in our simulations here using SPICE. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. Keep in touch for the new videos on our channel, subscribe, and if you also share and like these videos, then we can reach more people. Thanks for your cooperation and see you next time in another video. Take care.